Good afternoon. Let's report the next lecture. And some people have requested that I try to do some proofs today, rather than just talking about mathematics. I'd like to, with your help, reconstruct some of the proofs, how we actually do mathematics, what goes into it. I should say, yes, I was planning to do the preparation this morning, and then some unfriendly people interrupted me with an alarm. And then same thing in the afternoon. So, the positive way is you have to actively participate and you have to help me. So, what I want to show is I will still ignore some details, but give you the conceptual ideas how you prove things. For Newton's method, if you want to find roots, so you have a P is the degree D polynomial, and I claim that you have, there exists, so all the roots are in the unit disk. That's the only thing I use. I know about the polynomial. I know the degree and some rescaling of where the roots are. Then the theorem is there exists a universal set from the degree D, S index D of 1.11D log square D points that find all roots of P. I will not get into how you find, or not in detail how you get this particular constant, but in principle up to a constant, I hope I can convince you that this is not too hard. And then I hope I can also talk about the number of iterations that are required, how you bound those. So, and I want to tell you what kind of mathematics is required. Some of it we have already discussed, and some we have not, and then I will introduce to you what kind of complex analysis is necessary. That paper appeared, I don't know, 25 years ago, and it was rather, it had an impact on the people in root finding. They wouldn't think that such a thing would be possible. But it is. And I've shown you some pictures of the dynamical planes for Newton's method. And one of the important things is when you look at these dynamical planes, you see that there are these channels. Here is a root, and it has channels to infinity in one or several directions. And when you see it, you observe something is going on that you want to prove. Okay, so without computer, probably, in the computer pictures, probably nobody would have realized that this is possible. But so in our field, we can make conjectures. Of course, you have to always think that computers are lying. But once you've proved your conjecture, then whatever the picture was, it helped you get an idea. Welcome, you just started. Now I'll make a brief recap in a few minutes. Vadim is a few minutes late. Then I'll recap for both of you. And we can. So the first step is two definitions. The basin of a root alpha is the set of points that under iteration, Newton's method is NP of the polynomial. You iterate n times, it converges to alpha. The basis is the set of points that converge to the root. It's open. It's quite easy to see. When you converge, then some nearby points will converge to the same root.
Was in the upper index above capital N?
This is the circ. So I write f circ n as the composition of some function n times. So that's Milner's notation.
Okay.
N is the number of iterations, and the circle is the composition.
Okay, sure. I usually just write N. So
People use different notations, but that's what I'm used to. So we have the immediate basin That's the connected component around the root. So the immediate basin, by definition, is connected, but there may be some other components of the basin that are floating around, which I don't know how to control. I only work with the immediate basin. Okay? Maybe that's step 0, that's the definition. And step 1 is a theorem. The immediate basin obviously is open and connected. So you can call it U alpha. The immediate basin is simply connected. In other words, it has no holes. And when we see a simply connected subset of the complex plane, which is not the whole complex plane, we immediately think of the disk in which theorem? Riemann mapping theorem. So, U alpha is a Riemann domain. So that's an old result, 1988, I think. The hardest part of this is the spelling of the person who proved it, Felix Przetycki, a famous Polish mathematician. I hope it's correct. In any case, if my handwriting is bad enough, then you won't find the mistakes.
Yeah, I think it's correct.
Yeah, so there are two. This is Felix Przetycki, his son Piotr is also a mathematician. I will not too much get into it, but I should mention there is Mitsu Shishikura, one of the big people in holomorphic dynamics, who wrote a more general conceptual version of this. He proved it also well in the 90s, 92 up to 2008, I think. He proved it in 92, but he never published it. In 2008, I published my book on complex dynamics, in which the paper is included. So that's when it was finally published. Which is a more general, more conceptual version of this is specifically for Newton. And what Mitsu observed is it really has to do with fixed points. So fixed points of the Newton map. Let me just write it. Newton of z is z minus p of z divided by p prime of z. What are the fixed points? The roots when, well, n of z is z. If p vanishes, these are the roots. Is that list complete or not? Not maybe. Infinity is a fixed point. A repelling fixed point. Multiply d over d minus 1, so things near infinity are drifting slowly away from infinity. No orbits that drift to infinity like for Weierstrass. Drifting away from infinity slowly. So maybe you should draw the arrows the other way. Things are coming from infinity slowly towards the finite part of the plane. To make that precise, if there is a disk here that contains all the roots, then outside of the disk, so if z is bigger than 1 in this normalization, that implies n p of z in absolute value is less than z. It's an easy calculation, I don't have to do it, but there's nothing in it. So from infinity you drift towards the disk, and then once you're in the disk, you lose control. For instance, if it has poles, they must all be in the disk, and then you may lose control. Things go to infinity or near infinity. But outside, it's pretty tight. And the reason, let me just make a remark why this is simply connected. If it were not simply connected, then you would have a bounded hole like so, which is not in the immediate basin. And you watch where this goes. And eventually, you must discover a fixed point in this hole or in the boundary of the hole. But the fixed points are either at infinity or in some other immediate basin. So you cannot reach the hole, so there is no fixed point available. And then there are no holes in the first place.
Can you identify no fixed points are available?
Well, we just discovered where the fixed points are. And if you have a hole, you have to prove, and I'll skip that every hole requires a fixed point. And, well, a hole is bounded pretty much by definition. So it's not the point at infinity. And if it were another route, well, I think it's an interior fixed point. So this is, you have to rule both of these cases out.
Isn't our basin is simply connected, so we don't have the inverse?
You have to prove that. And that's exactly what we are trying to do. Okay, so it's simply connected, it's the Riemann domain. And then there is a Riemann map. Let me call it phi alpha from the immediate basin to the disk. We can normalize it so that phi alpha sends the root to the origin. And then it's uniquely defined up to rotation. So that's the Riemann mapping theorem. So we have the Riemann map, the root goes to 0. And that way we get a map F from the disk. This is the map. We start on the disk with the inverse of the Riemann map. Now we are in the immediate basin. Then the Newton map sends the immediate basin to itself. And then we go back here. So this is a map from the disk to itself.
But if we consider this basin on the Riemann sphere, like those branches, they should touch on infinity.
Aha!
It doesn't look simply connected then.
Infinity is not in the immediate basin.
Oh, it's
on the boundary. But the point at infinity is a fixed point, so will stay there forever and will not go into the finite complex plane. Okay. So we have a map from the disk to itself, and it has the property that if Z in the disk goes to the boundary, that implies that the image also goes to the boundary. When we are very near the boundary, we are near the boundary here of the immediate basin. Then the image here goes near the boundary of the immediate basin, and then we go back here. So I promise the we can. At the point when I think now we are complete for the day. So today, as we discussed earlier, some people wanted to see actual mathematics, not talking about it, but doing some mathematics. And I'm trying to prove something. I'm trying to prove, for Newton's method, the existence of this universal set of starting points, and possibly also the number of iterations that are required. And all this is a nice application of methods from complex analysis, like the Riemann mapping theorem. And it all starts, the basin is the set of points that converge to the root. The immediate basin is the connected component that contains the root. There may be some components of the basin out near infinity which are not connected to this. I ignore those. But if somebody has an idea how we can use them also, this would improve the bounds. I'm trying to find points here. This is my starting points in the immediate basin. Maybe we can take a few points less here and find them there. I don't know how to do it, but maybe some of you find an idea. The immediate basin is a Riemann domain, so we can send it by holomorphic to the disk, and then we get a proper self-map from the disk to itself by conjugating it with this map phi. Right? We're somewhere on the disk, go back by phi into the immediate basin, the Newton map goes in the basin, and then we send it back. So it's a holomorphic self-map from this. Okay? But if you have a proper holomorphic map from the disk to itself, it must be a rational map. One way of saying it is we can extend it f of 1 over z bar, complex conjugate, is 1 over f of z complex conjugate. That's called Schwarz reflection. So we define the map at a point outside, reflect it by 1 over z bar into the disk, apply f, and then we reflect it back out. And the theory of Schwarz reflection says that if this map extends continuously to the boundary, and we've shown enough that this is the case, then in fact you have a holomorphic map everywhere on the Riemann sphere, and that's a rational map. So here we have a global rational map which has a fixed point, the fixed points at 0. And then by reflection there's also a fixed point at infinity. Everybody in the disk will converge to the origin. So by symmetry, everybody outside will go to infinity. And then we are more interested in what happens on the boundary. So we define by M the degree of f restricted to, well, of the rational map. The degree of f, which is as a rational map, which is the degree of f restricted to the disk, which is the degree of the Newton map restricted to the immediate basin. Here we are using the fact every proper map has a degree for domains in the complex. And this degree is, of course, at most d, but it can be smaller. And in fact, it's at least 2. At most d, because here the Newton map is rational of degree d, the global Newton map. Why is the degree at least 2? Well, let me say if we have a simple root, if the root is simple, then it's super attractive, so it's a critical point. And that means already here the map is non-invertible. And therefore, well, if there's a critical point, then there's a critical point here. And in the general case, you can check it also, but let's assume the root is simple to make life easier. Okay? So, every point, you have a rational map of degree n. How many fixed points does it have?
N minus 1.
At most.
Ah.
Not exactly.
And minus 1 counts multiplicity.
Well, let's always count multiplicity. But a rational map of degree m, it's not m plus 1 is not the exact right answer.
What minus 1? Minus 1.
M minus 1 is not the right answer.
Okay.
I'm talking about the Riemann sphere, right? This rational map is naturally defined on the Riemann sphere. It's better. But just closer to the correct answer. It's not. Well, let's make the calculation. So, f of z equals, well, some different, it's a quotient of two polynomials. And in general, they have degree d. Right? Equals z. That means that's a fixed point equation. So what do you have? P of z equals z times q of z. So in general, the degree is d plus 1. And if you say, okay, but there are cases when the degree of q is smaller than d, well, then you get fixed points at infinity, which you have to count separately. So the answer is there are m plus 1 fixed points. Think of a quadratic polynomial. It has two fixed points in the complex plane, but there's always the one at infinity. Okay? So we have m plus 1 fixed points, and then overall. Two fixed points we already know. One is at 0, one is at infinity. So how many of them are on the boundary of the disk?
minus 1.
Now we are back to m minus 1.
M plus 2 minus 2. M plus 1 minus 2.
Exactly. It's m minus 1. So if a degree is 2 of the rational map, then we have 0 and infinity, and the circle maps to itself with degree 2. And when you have a degree 2 circle map, you have exactly one fixed point. Okay? So, we have some number of fixed points, m minus 1 fixed points here on the boundary of the disk.
You said if we have the degree of q polynomial is less than m, there can be separate infinite point roots. Yeah. Separate roots on the infinity. Or?
No, roots. Roots are. This is a polynomial in C, and the roots are in C.
No. When we counted the fixed points, the amount of them. We said that we need.
In this calculation here.
Yeah. And you said if it's equal to m, there maybe the few of them are different on the infinity, and how it is placed out. Yeah.
So then let's do this more carefully. So p of z over q of z is z, and the degree of f is the maximum of the degrees of p and q.
Yes.
So p of z equals z times q of z. So this thing has at most d plus 1 fixed points.
Yes.
Has at most degree d plus 1, therefore there are at most d plus 1 fixed points.
Yes.
And in fact, if q, there should be co-prime, if q has degree exactly d, then we have d plus 1 fixed points.
Yes.
If q has degree, say, d minus 1, then we have d fixed points in the complex. The rest is here. It's a bit of a, it's not very difficult to check, but I'd rather do the interesting things, and that's a little exercise. Make sense now? But now, so this map F has m-1 fixed points on the boundary, and m-1 is at least 1, because m is at least 2. So the boundary of the circle is the boundary of the immediate basin. Where do we find the fixed points? Here, the fixed points are the roots. And the roots here is, if there is a root, then there's an open neighborhood, and it cannot be on the boundary.
Sorry, could you repeat that last part?
So, the map F has m-1 fixed point on the boundary. It's at least 1. And now we go to the boundary of the disk. Well, the disk corresponds to the immediate basin. So the boundary of the disk corresponds to the boundary of the immediate basin. So we should find m-1 at least 1 fixed point on the boundary of the immediate basin. What were the fixed points of the Newton map? I mean, there are the roots, we checked this earlier. So if we have a root, then it has its own immediate basin. And the root is in the interior of the immediate basin. So it's not on the boundary there.
So it's an interior point, every such point.
Well, no. So yes, this root is an interior point of its own immediate basin. And therefore it's not on the boundary of the immediate basin that we're looking at. Contradiction? What's wrong?
m-1 equals 0, which means
m is at least 2.
Oh.
Well, we still have infinity.
Ah, we have infinity. Infinity is a fixed point.
Yeah, it's boundary. Yeah.
Right? So in this case, we have 1 fixed point here, 1 fixed point here, and 1 fixed point here. It's the same point at infinity for the Riemann sphere. But this immediate basin has 3 boundary fixed points. So I've drawn, well, maybe I should just restrict to the 3 that we have here. That means m in this case is 4. So if we start at some point and go around 4 times, we will, well, if you go around once, the image will go around 4 times, and we will pass 1, 2, 3 fixed points. So if we start on the boundary here, go around, then 1, 2, 3 times I will reach a fixed point. It's always at infinity. So that implies that each immediate basin U alpha is unbounded in m-1 direction, so to speak.
Question, but when we extended when we said that f is rational, we used that it is it continuously extends to the boundary. But like if
did we use that?
But how then we extend it to how then we inflect it into the...
Okay, so one of my plans didn't work out. I was trying to sweep it under the rug. Does the map, well, F or phi, which of them extends continues to the boundary? Well, F does, maybe yes. So F does, phi may or may not. But F extends continuously to the boundary. Yeah, that's because it's a proper map. Okay, then ask your question again.
But if f extends continuously, then we can reflect and
So we always can. This is called transreflection. And if you look at it properly, all you need is that if z goes to the boundary, then f of z also converges to the boundary, which is weaker than saying f extends continuously to the boundary. This is a somewhat stronger version of Schwarz reflection, but that's all that's required. Which is a dilemma from complex analysis, which I could have introduced, but I'm using it, and this is the version. And it does work. There are no miracles here. Okay? So I have m-1 boundary fixed points, and each of them corresponds to a fixed point at infinity. So the number of channels that I get to infinity is at least 1. And in fact, it equals the mapping, well, 1 mapping degree minus 1, which means it equals the number of critical points that I have here or here. One critical point is the root, which, if it's simple, it's a super attracting fixed point. And so if you have a single root, well, if you have a single root, the mapping degree could be 2, so there is 1 boundary fixed point here. And you get extra channels to infinity if you increase the mapping degree of the immediate basin, which means if you increase the number of critical points of the Newton map. And the Newton map derivative is p over the pp double prime over p prime squared. The critical points are the roots of p or roots of the second derivative. And now we discussed a few sessions ago, I had marked in the Newton pictures the roots of this guy. Somebody of you had observed, and this is the case every time you have another root point of inflection if you wish, in the immediate basin you get 1 more channel. And now I've just about proved that observation. Okay? So these are my channels. I have channels to infinity. And now what I want to do is measure some channels you see in this are, I've drawn them too similar. Some are pretty narrow, and some are more wide. And I want to prove something like they are wide enough that my universal set of starting points is a grid like this. And I have a certain width of points, and the channels I want to show that are wide enough, they're not, at least one of the channels is not too thin. And that way, one of my points will intersect this the immediate basin. So I have to measure somehow how wide they are.
So that decides like our sampling rate.
Exactly. So let me tell you how we measure this. And I wish there were something. People asked me the other day, can you also have a universal set of starting points for the Weierstrass or other methods? Oh, how much I wish. Yeah, so this is for you to do. I don't know the proper mathematics to make it happen. I know it in one dimension, I'll show you. But maybe you can invent some mathematics generalizing with this idea that perhaps gives us some idea on this. Okay? So, I take a large circle near infinity. Well, if this is the disk, I should be further out. And then the circle maps to a smaller circle, and in particular, I cut out some kind of rectangle from the immediate base. So, this thing here, in fact, the dynamics glues this part to this part. The dynamics is a cylinder. So I can roll it up. You have to leave. Well, whatever your preferences are, have fun with your class, with your exam. Same to you. Good luck.
I will. I don't know if I see that.
Very good. Yes. So don't run away from Guillermo.
But I need to be there a minute earlier, so.
Well, whatever. If you can stay, then I don't want to kick you out. Okay. So this is now a doubly connected domain.
We take this this curve, and then we apply the dynamics. So one iteration of Newton map, and we get this another one.
Or we could also say we just take some domain like this, and we take the quotient by the dynamics, so we quotient out the dynamics. So this point and this point and this point and this point is the same. And then the quotient is naturally a topological cylinder. Okay. And I want to measure the thickness of the cylinder. Out here, the Newton method is something like near infinity, z maps to d minus 1 over dz. So I know this distance from here to here. That distance near infinity, the Newton map is easy to compute. So I want to know how long this cylinder is.
So this is the asymptotics of Newton method near infinity, right?
Which is easy to compute. So how do I have Newton somewhere? Newton is z minus p over p prime. But this really, if this is z to the d, then this is d z to the d minus 1. You cancel those, and there's just one z minus z over d. D minus 1 over d times near infinity. So near infinity you have good control. So this bit I know, but I want to see how wide this is. And here we know the Riemann mapping theorem for a simply connected domain. It's generally just a disk. If we have any doubly connected domain, then there is an annulus, standard annulus, between radius r and 1, r is less than 1. So that this is biholomorphic for a unique r. It's not very hard to prove from the Riemann mapping theorem. It's in the appendix of my book, but maybe that's something classical, something that you can believe me. So, and when you take, well, this now I can take from here a log, then this is a rectangle. I cut it open here between imaginary parts I pi and minus r pi and plus I pi. And the real part is between log r and 0. And I have to glue those two bits.
And this r will depend on the size of this initial.
Exactly. So some are fatter than others. And there is a unique r. If you change the r, it's not conformally equivalent. But you see that this guy, by taking a log, then the log turns absolute values into real parts from log r to 0. And then the angles go from minus pi to plus pi. It's this thing.
So it's like from polar coordinates back to.
That's what the log does. And it's rolled up here. So it's really a cylinder of height log r, and the circumference is 2 pi. So this guy has a modulus, which is height, so in this case it's log r over 2 pi, while r is the unique one from this term. And that's a biholomorphic invariant. If you have biholomorphic coordinate changes, the modulus is well defined.
What is mu?
That's just the modulus. I define it that way. I define it the modulus and I call it mu. Okay? And here is a particular annulus for which I can make this apply. So I want to compute the modulus of this guy and then make estimates on it. Okay? So unfortunately I need a bit of fresh space. Good luck with your exam. See you tomorrow.
You can raise things.
Okay. So, how can I do that? Let's look at this picture here. And I just draw a blow up. I don't need as much space. Here is a fixed point, Q plus. And the rational map after I extend it is holomorphic. So there is a derivative which we call lambda, f prime, is well defined. Lambda is not only defined on the disk, but everywhere on the Riemann sphere, in particular here. Okay?
This is this line.
It's this bit here. I just don't want to draw the full disk. But here, this is the disk. And here I have the map F on this side and F everywhere. Okay? So, now I claim that this multiplier must be positive. A priori it's a complex number, but if F should send the disk to itself, should send the complement to itself, so it must send this tangent line to itself. And that makes the multiplier real and positive.
To basically use that equality from reflection.
Yeah. Well, after I've used that, I have the map. If it's holomorphic, and then I used it in order to extend the map. But by the time I've extended, I don't need it anymore. And it's just the disk goes to itself in the complement. Okay? And better yet, is holomorphic greater than 1? Because if it were less than 1, then it would attract orbits from both sides.
And we know that this does not happen.
Because all the orbits go to 0 and to infinity. Now you could discuss what happens when it's equal to 1. Parabolic fixed points are a bit subtle. We can rule them out also. So it's bigger than 1. Okay. Now here I do the same thing that I did here. I take some neighborhood within the disk and take the quotient by the dynamics. In this case, F. So, this channel out to infinity is in some sense within the immediate basin and neighborhood of the fixed point. So the image under the Riemann map is a neighborhood in the disk of that fixed point. Okay?
Okay, can you say again? What do you mean that neighborhood?
Here I have the disk, and perhaps I can make it even go all the way out. I just cut open the immediate basin, and I take everything above. Outside of the disk, so the dynamics is injective and drifts towards the disk. And then here I have the Riemann map, phi, and then the neighborhood, or the part of the immediate basin, which is a neighborhood of the fixed point infinity, becomes a neighborhood of this point, Q. Okay? So here, the cylinder is constructed as the quotient of the blue part by the dynamics. And so I take the quotient by the dynamics. Okay, and now let's blow it up. I can make it very small and say, so it's just blown up very small. The boundary is now just a straight line. And then if I take a semicircle, it is mapped, say of radius rho, it maps the semicircle of radius lambda times rho. So the quotient by the dynamics is really the quotient of the semi-annulus by the dynamics. Right? And I can compute it again by taking a log. And then what do I get here? The real parts go from log, or the real parts are first log rho to log rho plus log lambda. And this goes minus I pi over 2 to I pi over 2. And I have to glue here.
To be like the right part of the semi.
Maybe about rotation or something. So again, this is a cylinder where the height is log lambda, and now this is pi. So the modulus, which I can call mu, is in this case pi over log lambda.
And why are they in reverse?
What?
Why are they inverse? So there we have log over 2 pi, and here we have pi over log.
This is a different situation. So here we are gluing. Don't confuse the two pictures. It is just treat them separately. It's not, I mean, here we have a full annulus, and here we have a semi-annulus, and here we are gluing along the circular direction, and here we are gluing in the radial direction. So, it's a different thing. But in both cases, an annulus or a semi-annulus becomes a rectangle. But the gluing is in opposite directions, and so the quotient obviously has to be in the different direction. Okay. But what we can do is, we conclude that I don't know the modulus here, which I want to find, but I know it is the same, it is pi over log lambda. So in order to compute how wide this thing is, I need to know something about the derivative of these fixed points. Okay?
And then we can go back.
By conformal equivalence.
So this is very important here, is that this modulus is invariant with like holomorphic.
Right, that's what we're using. And there's a whole mathematical theory called conformal invariance. This is one of them. There's a famous book by Lars Alfors, field methods, first generation, conformal invariance. Okay?
Q is associated to the infinity in the last picture.
In one particular channel.
Yeah, so
If I take different channels, I get different fixed points, different derivatives.
So you need like the limit of derivative as the point goes to the channel.
Well, in the channel, the derivative at infinity, I don't really see it. I compute the derivative once we are on the boundary of the disk. In the plane, the derivative is something like d minus 1 over d or so. but that is not,
But it changes so we can.
yeah, it's not, it is invariant in open domains. But here you are on the boundary, and then you can, and the boundary is not respected. Okay? So in order to compute how wide the channels are, we need to compute the derivatives of these boundary fixed points. Okay? And now we use one of the fundamental theorems in complex analysis, the residue theorem. Who of you has heard of the residue theorem? Half of the people. 2.5 out of 5. So let me try to kind of not state it explicitly, but just look at it and use it. So I use the function g of z is 1 over z minus f of z. If f is a rational function, then g is also a rational function. And the poles of g are the same as the fixed point of f. So that's a nice tool to analyze fixed points. But all of you, so you have taken, who of you has taken basic complex analysis? You have taken some.
Yes.
So you know about holomorphic line integrals?
Yes.
Yes, so this is, let's look at a fixed point. G is holomorphic with the fixed point at 0. So here's the fixed point, and now I draw a loop, gamma, around this fixed point. And I compute a co-residue at the point A of G, that's the integral along this closed curve gamma of the function G. Is this a residue? Yeah, I think it's just, this is maybe 1 over 2 pi.
Yeah, I think 1 over 2.
Yeah, this is the kind of thing everybody forgets, except you. Yeah? And the point is, it doesn't depend on the curve. And what you need to know, a residue of 1 over z is just 1, which is an it's an integral along a finite curve, compact values. But then it's more complicated. But this is not the case of interest to us. And now we look back at this situation. We have too many fixed points on the boundary of the disk. And here is a fixed point at the origin. In the index, it's 1. The derivative is 0. The super-attracting fixed number is 0, so 1 over 1 minus 0. The index is 1. That's easy. Now if we compute a very large curve like so, then we have to check it. This happens to be now I have to make the preparation. I think it's 0. If you're very far near infinity, you have to check it. Which in principle you can change coordinates, or you can just near infinity here make the calculation. What f is, what g is. And I think it comes to 0.
Do you mean that we take the integral over this?
Over a very large circle.
Okay.
For the function g, yes.
I have to go.
So you and then it's an easy exercise, and I would have liked to have prepared it in a bit more detail. But in principle, this is not hard to check.
The idea there that we get like 1 over the radius.
It's just and the radius is large.
Which is raises at infinity, right?
Yeah, well, you have to say in which coordinates. In principle, infinity is a super-attracting fixed point also. So you have to. I'll leave this as a homework. It is easy, but you just have to make the computation right. So, and now the point is that there is some calculus with these curves. I can break up this large curve into. The integral is homotopy invariant. So if I change the curve slightly, the value does not change at all. But that's part of what you prove in basic complex analysis. So therefore, the curve, when you get proof 0, you show when the curve is larger and larger, the value is smaller and smaller, closer to 0. But it's constant because the curves are homotopy. And therefore must be actually 0.
And also we shouldn't cross the fixed points of
We should not cross the singularities. But there's no fixed point between radius 1 and infinity. So now I break it up, this thing, into 3 curves. One curve is this one here. Then there's the second curve here. And the third one here, and the last one there. So, you can always, as you say, we must not cross where the poles are. Or if we do cross, we have to keep track of what it is. So these 4 curves keep track of what it is at the poles. Therefore, 0 is the integral for gamma large, is the sum of the residues at fixed points in C. Which is one of them is 0, that is 1, plus the sum of the residue on the boundary of the disk. Now I have to erase something. Maybe I erase here. Like it?
Yeah, it's already gone.
Very good. So, therefore, the sum on the fixed point on the boundary of the residues of, what is it, 1 over 1 minus lambda equals minus 1. Right? Let's change signs. 1 over lambda minus 1 equals plus 1. It's easy to compute with positive signs. So, and there are, how many terms did we compute here? M minus 1, I guess. M was the mapping degree, and there's M minus 1 boundary fixed points. So we don't know, so these are the lambda I. Therefore, we don't know what the values are, but there exists a lambda I, so that 1 over lambda I minus 1 is now, as you wish, smaller or bigger than 1 over m minus 1. If the sum of m minus 1 terms equals 1, then one of them must be larger or smaller than the average. So there exists a lambda so that lambda I minus 1 is bigger or smaller than m minus 1. So lambda I, in this case, I want to be smaller. There is one of those things where the lambda I is less than m. Okay?
Bigger or smaller, it's very nice. Binary.
I never remember at this stage. You can choose. But I mean, this is.
Yes,
Somebody has to be bigger or smaller than the average.
Everything's accurate.
So there exists a lambda I which is less than m. That means mu I, which is pi over lambda I, over log lambda I. No, let's start here. Mi, which is pi over log lambda I. Lambda I is less than, so this is bigger than pi over log m. So we have found a lower bound for the modulus of these guys, which is bigger than pi over log d. So for those that have a single channel like here, it's pi over log 2. That's easy, but there can be many channels, and some may be very thin, that's a big derivative. But there is at least one which is sufficiently wide, pi over log d. Okay? So, and let's go to this picture here again. We have our fifth channel where the modulus is at least pi over log d. We know this thing here is something like 1 over d. So some universal annulus, or depends on the degree perhaps. So, in principle, you could try to compute if you have so many points here, have enough points, then of course the annulus, if you want to avoid it, that means the channel has to do some gymnastics like so. But if there are too many points, then this gets very narrow, and then you don't accomplish pi over log d. So, if you are good at computing conformal invariance, you could calculate that. I'd rather tell you my lazy solution. The lazy solution of our paper. But here I have to use one more trick. I don't use one circle, I subdivide it into log D circles. And that way, what I used to have a modulus, it breaks up into mu1 and mu2, mu log, I have log D subannuli. If I have log D circles. Don't tell me, well, then there's perhaps one more or one less, so I ignore those. And now they are a bit like capacitors. 1 over the original modulus that I have relates to the sum 1 over mu I. If you've seen capacitors in sequence, then this is what you get. You have to look a little bit into how this is computed. This is not difficult. Bit of standard routine. And in fact, you can, all the conformal analysis is a lot related to electrostatics. And we really compute the capacity of these domains. But maybe I will import this result. And now I'm not sure which is again. Some people remember it and some don't. But the outcome is that one of those is bigger than the number of circles that I have times the previous one.
And what's the previous one?
So here we have one which is at least pi over log D. And now we break it into log D parts, and then this inequality goes the right way.
So mu is just big region, and for one of the subdivisions.
Yeah. I mean, in principle, if you... So you have a cylinder like so, and if I break it up into sub-cylinders, then for the sub-cylinder, the height is the same, but the circumference is divided by the number of pieces. And therefore, for the sub-cylinders, height over circumference increases by the number of pieces. Of course, they're not all the same, but you have to check the inequality goes the right way. And therefore, it is pi. We have pi over log D, we have log D pieces, and then it's pi. So that's the lazy version. You have to know there's an inequality. And so what I do is I cut this annulus into log D pieces. And I know that in one of them, I must find an annulus that can get narrow, whatever it is. But it's a universal problem. But once I know the scaling, then there is, so let me move over to the next board here. And I draw this, well, maybe I draw another log, so the circle becomes a vertical line. So from here to here it's a log, it's an infinite vertical line. I want to distribute my points here, enough of them so that I hit a channel with modulus mu. So that means the grid of circle points becomes a vertical grid like so. And so then the distance here, if the factor, here the factor is multiplication by d minus 1 over u. So here the factor is multiplication by d minus over d times log d. Right? No, this is, let me know, this is no vote. This is no vote. Let me go move it easier in these coordinates. I have the log d times like so. And then here was multiplication by d minus 1 over d. And that means this whole distance is plus log over d minus 1 over d, which is approximately plus minus 1 over d. Going before, I should do the subdivision there. Here I have the inner circle, the outer circle, factor d minus 1 over d. When I take logs, multiplication becomes addition of the log. And log d minus 1 over d is something like 1 over d. So this distance is 1 over d. And now I cut it into log d pieces. So this guy is 1 over d log d. The distance here. Can you follow?
I try.
So, can I help you?
So we take this part somewhere in the neighborhood of infinity, right? So this is somewhere far away.
No, this is between radius, say, around radius 2. 2 maps to 2 times d minus 1 over d.
So our circle will be like r e to the I pi something. And when
The r is 2 here, and here r is 2 times d minus 1 over d.
Okay, so when we take the log, we have the constant real part, and the imaginary part changes from vertical.
Yeah, the circle becomes a vertical line, and these two circles, which differ by a factor of d minus 1 over d, after the log becomes horizontal distance, essentially 1 over d.
And multiplication translates to addition, so we have...
Exactly. So therefore, the horizontal distance from the leftmost to the rightmost is 1 over d.
I still didn't understand that part, like that z goes to d minus 1 over d, that's not for big z, isn't it?
For large z, yes.
For large z, yes. And how do
So,
you know?
maybe for your radius 2 it's not good enough, and you have to check for radius. If you feel safe, take radius 100 and estimate the error.
I think it's a good exercise. So to write the Newton's map, we know that we know the degrees, and to calculate the asymptotics.
So z, at least
so we have
1 over d plus some small constant.
Yes, yeah. So
we can
I
approximate
ignore.
it without problem.
Yes, if we are sufficiently far away from the disk, it converges to 1 over d. And if we're not quite so far away, we have to make some estimates.
But it's like a constructible proof, so we should
Yes.
actually do those separate approximations.
Yes, so, and in the paper, I think we use radius 2, and then we say, well, it may not be exactly 1 over d, but between a factor of 1/2 of whatever. You can make precise estimates, which I'm sweeping under the rug. But you see that the Newton map here says this circle, this is not an exact circle, but approximately. So in log coordinates, it sends this line to this line. The distance is 1 over d, and now I add log d intermediate lines. So that the distance between any two consecutive lines is 1 over d log d. Okay, and now on this line, I want to find, actually, let me change coordinates once more. I multiply by d log d. then the horizontal distance is 1. And here I will distribute so many points. When I'm trying to find the modulus with pi over log d here, then I use this capacity inequality. So therefore, I need to find a modulus which can try to hide away from the points, but it's a universal question. You have a conformal quadrilateral cylinder that connects this side to this side, and the modulus is at least 1 or some constant. And if you make it too narrow, you will never get to 1. So there is a universal constant for the spacing of those points. I could compute how, and you get elliptic integrals and such. It's a beautiful thing. But up to precise calculations, it's a pairwise distance, it's a universal problem with 1 modulus 1. If the points are spaced too close to each other,
You won't get this.
yes. So therefore there exists a universal spacing delta, so that if the points are less than delta apart, you must find the modulus.
It seems just very interesting that if we just try to draw something like this, we probably could, but this restriction of like holomorphic map won't allow us in some sense.
With the condition that you want to avoid this grid of points.
Yeah.
So there is a universal delta, which I have not computed. And that means in this scaling, the distance between those points here is delta over d log d. Of course, this is an infinite strip, but we want to go around only once. So the number of points that we have here is 2 pi divided by delta over d log d, and that is 2 pi d log d over delta. And of course, we have log d circles. So the number of points is constant times d log squared d. That's the theorem. So here there is a bit of complex analysis that I have not defined for you. This is the general area of length area inequalities. But other than this, I hope you see what we are doing in order to find, and then I think it's a complete proof up to constants.
Yeah, we can imagine what technicalities are left.
Yeah, I don't want to get into technicalities, but somehow I was trying to hit a line. You wanted to see, we discussed that the other day, you wanted to see some actual proof.
Yes, what I mean, we can see the main idea and at the same time how you do all this.
Yeah, so it's not over complicated at all, and like many classical ideas from complex analysis, very, very nicely put together.
Yeah, and I wonder was there a concept of this index of a fixed length before this proof, which is like this residue.
Yeah.
So it was like if
that is known before.
So it's about how many times you go around this point, I think, right?
Well, you only go once around, but still the index checks what multiplier you have, with the lambda. So that has many interesting applications in its own right. We didn't invent the holomorphic fixed point index, but it came in quite useful.
So for practical,
that was like the most interesting.
So for practical reasons, it would be very nice to know this delta, right? And what can you say about that?
Okay, so I mean, now you want to know the constants. Let me give you a little bit. One thing is, you don't need to use log D circles. How about 3 log D circles? So you throw in a constant in front of the log D, and then you get out a different delta. And everything depends on, so you fix the number of circles constant times log D, and then you compute the delta that comes out of it. And if I remember correctly, the best number of circles is 0.66 log D circles. No, this is not enough. And then on each of them you have 4.1 D log